Welcome to this explainer. Have you ever stood in front of a massive modern industrial plant and just wondered, how does this whole thing not collapse into absolute chaos? Well, it really helps to stop thinking of a plant as just a giant pile of pipes, valves, and wires and start looking at it like a highly complex living organism. For this massive organism to actually survive and, function safely at industrial scale, it needs a perfectly integrated nervous system, incredibly sharp sensory organs, and a brilliant, fast-acting brain. So let's unpack exactly how that anatomy is built.
Okay, let's dive right into this macro to micro tour. We're going to cover the anatomy of a digital plant, look at networks and redundant systems, check out the field-level digital evolution, tackle safety and hazardous environments, and wrap up with simulation and digital twins.
Right, starting things off at the absolute macro level. To understand the basic skeleton of plant operations, the anatomy of a digital plant.
So if you break down the hierarchical architecture, it distinctly separates process control from the physical variables on the ground. Think of this as the four main tiers of our organism's anatomy. Way down at the bottom, you have the field level. These are your sensors and actuators. They're the physical senses actually touching and feeling the process. Move up a step and we hit the control level. These are the controllers sitting near the process, acting kind of like the autonomic brain, making constant micro decisions. Above that sits the server level for scaling everything up, and finally, right at the top is the operation level. That's your central monitoring control room where the actual human oversight happens.
Now, to keep that massive four-tier structure running smoothly, engineers rely on 5 core foundational blueprints. Everything is completely built around central operation, central maintenance, and central engineering. Basically, that means you control, fix, and build everything from one unified place. But the last two? They're arguably the absolute most critical for survival. Fail-safe systems that trigger a safe shutdown when things inevitably go sideways, and high availability to make sure the plant almost never has to stop in the first place.
So that begs the question, how do you engineer all of this without spending literally decades programming individual valves? Well, the secret sauce is control module types, or CMTs. If the architecture we just talked about is the skeleton, CMTs are the DNA of the digital plant. They are these incredible master blueprints that set the uniform rules for exactly how individual components behave, allowing them to be instantly replicated throughout the entire system.
What's really interesting about this in practice is how changing one primary CMT instantly updates everything else. Let's say you suddenly realize a specific type of valve needs a new alarm parameter. Instead of going in and manually reprogramming 3,000 individual valves, which, let's face it, would take an eternity, you just tweak the primary CMT blueprint once. Boom. Instantly, all associated instances across the entire plant are synchronized and updated. It saves a massive amount of engineering time and completely eliminates a whole lot of human error.
Moving right along into the nervous system of the plant, let's look at networks and redundant systems and see how data survives inevitable physical failures.
Redundancy is really how a plant guarantees continuity. Think about it like driving down the highway. If your car's primary speed sensor faults, you don't just lock up the brakes and stop dead in the middle of the interstate, right? Your car seamlessly switches to a backup path so you can safely get to a mechanic. Well, the digital plant works the exact same way. If a primary network path breaks, the system absolutely does not shut down production. It simply shifts the data over to an active secondary path.
Processing all that redundant data naturally requires some serious hardware. We can really break down this controller matrix by comparing the heavy lifter with the more specialized unit. The AS410-5H is your massive, highly scalable brain designed for large-scale standard process automation. But if you have a smaller application that still desperately needs high availability and fail-safe redundancy, you drop in the CPU410E. It's essentially the rugged, cost-effective, fixed-scale alternative, but it still speaks the exact same digital language.
Now, connecting these big brains to the human operators requires incredibly disciplined traffic management. Industrial Ethernet solves this by cleanly separating the traffic into 2 distinct highways. You've got the terminal bus, which connects the operator clients to the servers using standard TCP/IP traffic, but underneath that, strictly separated, is the plant bus, linking the servers down to the raw automation systems. Keeping these two completely isolated ensures that someone running a heavy database query in the control room doesn't accidentally jam up the real-time commands that are keeping a high-pressure reactor stable.
When it comes to actually laying down those network cables, engineers have to balance cost, speed, and resilience through different topologies. You have line geometry, which is simple and cheap, but if a cable breaks, you're totally disconnected. Star geometry gives you great performance and isolates failures pretty well. But the absolute gold standard for process automation, that's ring geometry. It features a special redundancy mechanism, so that if a cable breaks, the blocked port instantly opens and the message just routes the long way around the circle. The network never splits.
All right, let's step down to the sensory organs of our operation. Welcome to the field-level digital evolution.
And this brilliantly illustrates just how far industrial communication has come. I mean, we started with conventional 4 to 20 milliamp analog wiring, which was clunky, point-to-point, and gave us almost zero diagnostic data. Then we moved up to Profibus, which brought in digital data transfer and modularity. Finally, we arrive at Profinet, the absolute leading Industry 4.0 Ethernet standard. It essentially takes the ruggedness of the past and injects lightning-fast, real-time capability directly down to the actual sensor.
So just how fast is Profinet? It operates with such intense precision that it tracks and sequences events down to 1 millisecond. Just imagine a scenario where an entire plant shuts down because hundreds of alarms are going off within the exact same second. With 1 millisecond timestamping accuracy, engineers can go back, look at the timeline, and trace the absolute true first message. They can pinpoint the exact root cause of the chaos instantly. It's a real game changer.
But speed isn't just about reading data. It's about healing the network. Remember that ring topology we were just talking about? Profinet uses media redundancy protocols, or MRP. If a backhoe accidentally slices through a fiber optic cable out in the yard, the MRP manager dynamically reroutes the entire flow of plant data in the opposite direction. And get this, it does it in a maximum of 200 milliseconds. The controllers literally do not even have time to realize a cable was cut. No blips, no downtime.
Now, let's shift our focus to physical safety, moving from digital speed to the real-world dangers in the plant. Section 4. Safety in hazardous environments. But what happens when the plant environment is explosive? It's a hugely critical question, because you can have the fastest Profinet ring in the world, but if your sensors are sitting in a giant cloud of highly combustible gas or reactive chemical dust, running a standard electrical signal right into that zone is, well, incredibly dangerous. This is exactly where intrinsically safe barriers come in. When you have a safe zone right next to an explosive atmosphere, you place an RS-485IS coupler right on the border. This device acts as an isolating transformer and a physical safety barrier. It limits the electrical signal entering the danger zone so strictly that even if a wire completely shorts out, it physically cannot generate a spark with enough energy to ignite those gases or dust. It's absolutely crucial for keeping the place from going up in flames. And because those explosive zones are so inherently hazardous, you really don't want your human engineers wandering out there to manually calibrate smart valves unless it is absolutely necessary. Thanks to central data management bridging the physical and logical layers, they actually don't have to. The network routing acts as this highly secure tunnel, meaning an engineer can safely sit in the control room hundreds of meters away, reach virtually through the system, and calibrate an intelligent field device without ever leaving their desk or interrupting the process.
Let's guide ourselves over to the final virtual stage of our map, Section 5, Simulation and Digital Twins, showing how the plant thinks before it even exists.
That specific capability is what we call a digital twin. Using software like SIMIT, engineers can create a complete, fully functioning virtual representation of the facility. If the controllers are the brain of our organism, the digital twin is its imagination. It allows the plant to run in a completely safe virtual world, giving operators the chance to detect, design errors, and literally train on catastrophic scenarios long before real-world production ever begins. When running these simulations, engineers typically use two distinct methods. So, the crucial point here is understanding the difference. Hardware in the loop, or HIL, connects the virtual simulation to actual physical hardware controllers sitting on a test desk, effectively testing the real processing system. Software in the loop, or SIL, on the other hand, is purely virtual. The controllers are entirely emulated in the software, which is just incredible because it unlocks advanced slow-motion testing and time-lapse scenarios that you simply couldn't do with real hardware. And this is where it all comes perfectly together in a completely unified architecture. You standardize everything using those CMT blueprints to kill off duplicate engineering. You design for failure using redundant MRP networks that heal themselves in milliseconds. You modernize the edge by driving Profinet directly down to the field sensors. And finally, you simulate the whole shebang using a digital twin to bridge the gap between initial design and physical production. It truly is a masterpiece of modern engineering.
Which leaves us with this final, rather provocative thought. If you can simulate every single failure before building the plant, Is unplanned downtime a thing of the past? We've seen the redundant networks, the lightning-fast data, the intrinsically safe barriers, and the virtual twins. As this digital anatomy becomes increasingly perfect and predictive, are we actually approaching an era where unplanned industrial downtime simply ceases to exist? It's a fascinating question, and one that is intensely driving the very future of automation. Thanks for joining me on this explainer, and I'll catch you on the next one.